Accuracy is useless when one mistake is 10 times more expensive than the other. I'll build cost-sensitive classification in scikit-learn so the model optimizes the decisions you actually care about. This is the pattern you'll be able to implement by the end, which applies explicit error costs to predicted probabilities, to choose a threshold, and return cost-aware labels. I'm Professor Pi, teaching AI foundations with simple Python. In practice, you meet cost-sensitive classification when the labels are imbalanced and errors have unequal harm. Think fraud detection, where missing a fraud costs money, or medical screening, where a missed disease has high human cost. A model that maximizes raw accuracy can still be useless. It will lean on the dominant class and ignore the expensive mistakes. Scikit-learn is a good fit here because it gives us probability outputs, simple ways to weight classes during training, and tools to search for thresholds or tune hyperparameters using cross-validation. Success in this workflow means the model makes decisions that minimize expected monetary or social cost, not just accuracy. That looks like fewer missed positives when misses are costly, or fewer false alarms when alarms are costly. On a toy dataset, this yields a measurable drop in expected cost. In a real system, it maps to fewer payouts, fewer wasted follow-ups, or better patient outcomes. We will show a full path from plain accuracy to a cost-aware, deployed decision rule. At an intuitive level, the idea is simple. A classifier can give you class probabilities. You then pick a decision threshold that translates probability into a label. If missing positives is expensive, you lower the threshold so the model calls more cases positive. If false alarms are expensive, you raise the threshold. You can also adjust the model during training by making positive errors more costly in the loss. Both moves push the final decisions toward lower expected cost, but they interact and need evaluation on held-out data. We will build a short project so you can see each step. We start with a skewed synthetic dataset and a plain logistic model to get a baseline. Then we compute the real cost at the default threshold. Next, we search thresholds to directly minimize cost. After that, we retrain with class weights and apply the analytic cost optimal threshold. Finally, we wrap it all in a cross-validated grid search with a custom cost scorer to pick the regularization that minimizes expected cost. That keeps the code approachable and the decisions explicit. Now we train a baseline model and measure naive accuracy. This snippet trains a scikit-learn logistic regression and shows plain accuracy on an imbalanced toy set. It creates a skewed binary dataset using make classification so negatives dominate positives. The train test split call preserves class proportions with stratify to make evaluation realistic. Logistic regression is fit on the train split and predict produces hard labels on the test set. Finally, accuracy score computes the fraction of correct labels without differentiating which mistakes matter. Because class imbalance can mask harmful false negatives or false positives, a high accuracy here may be misleading. The printed accuracy is a naive baseline. We will improve by optimizing decisions for cost. Next, we measure the expected cost using the model probabilities at the default 50% threshold. This example computes expected error cost at a fixed 0.5 threshold using scikit-learn probabilities. The predict_proba function, which returns class 1 probabilities, supplies a score for each test point, and we convert those scores to labels with thresholds set to 0.5. We define cost FP for false positives and cost FN for false negatives to reflect real-world stakes. The variables FP and FN measure average rates of those errors on the test set, and cost combines them linearly by their penalties. Increasing cost FN raises the price of missed positives, while increasing cost FP punishes false alarms. The printed cost shows how expensive the default threshold is for this problem. Then we search over thresholds to find the one that minimizes expected cost on the test set. This code searches thresholds to minimize cost and reports the best value with its cost. It starts from the predict proba scores and defines a grid of thresholds with NumPy linspace. For each threshold, it turns scores into decisions, measures false positive and false negative rates, then builds the total cost using cost FP and cost FN. The list of costs is scanned with argmin to find the optimal threshold and corresponding minimum. A denser grid improves precision but takes longer, while a coarser grid is faster but less exact. The printed threshold is the simplest actionable rule that minimizes expected cost on this test set. After that, we retrain the model with class weights and apply the Bayes optimal cost threshold analytically. This example fits a class-weighted logistic regression and applies the Bayes optimal cost threshold. The class weight mapping nudges the loss so the positive class's errors weigh cost FN times more than negatives. After fitting, predict proba supplies calibrated like scores, and T star uses the closed form CFP over CFP plus CFN rule for minimal expected cost under symmetric priors. Decisions come from comparing scores to T star, and cost is recomputed from observed false positive and false negative rates. Increasing the positive class weight or decreasing T star both push the model toward recalling more positives, often lowering cost when misses are expensive. The printed cost shows how weighting plus the analytic threshold reduces error expense. Finally, we tune regularization with cross-validation, using a custom cost score that reflects our penalties. This snippet runs GridSearchCV with a custom cost scorer to select C that minimizes expected cost. It defines T from the cost ratio and builds a make scorer that returns negative cost, so lower is better for the search. GridSearchCV evaluates logistic regression across C values with cross-validation using predict proba and the scorer's thresholded decisions. After fitting, best estimator is applied to the test set, and the final cost is computed with the same decision rule. Increasing C reduces regularization and can fit costs more tightly, but may overfit. Decreasing C smooths decisions and can raise cost. The printed result shows the achieved test cost and the chosen C. This toy workflow maps easily to production. Replace the synthetic data set with your real features and labels. Use a validation split to set costs and thresholds that reflect billing or downstream workflows. Log the resulting expected cost and monitor it after deployment. Recap what it is: a way to make classifiers care about the actual cost of mistakes by adjusting thresholds and training losses. When to use it: when classes are imbalanced and the harm of false positives and false negatives is different. One caveat: optimizing for cost on a single held-out set can overfit. Always validate with cross-validation or an out-of-time split. Next step: tune the regularization parameter C more finely with nested cross-validation. Or expand the threshold grid around the best value to squeeze out lower cost without overfitting. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.